Deep networks are hard to train because of the vanishing gradient problem. As the gradient is back-propagated to earlier layers, repeated multiplication may make the gradient infinitely small. As a result, as the network goes deeper, its performance gets saturated or even starts degrading rapidly. The authors of ResNet argue that stacking layers shouldn't degrade the network performance because we could simply stack identity mappings upon the current network, and the resulting architecture would perform the same. This indicates that the deeper model should not produce a training error higher than its shallower counterparts. And some people say that this residual block is like a differential amplifier and it amplifies the signal. Seems reasonable as well. Many people try to give ResNet an explanation and they hold different ideas. The core idea of ResNet is introducing a so-called identity shortcut net connection that skips one or more layers as shown in the following figure. A feature map goes through two conf layers and then there is another identity shortcut and we add those two together. Before this, we only have the fx function, and ResNet not only use fx but also adds the original x to it. It's trying to learn the residual. Because of its compelling results, ResNet quickly became one of the most popular architectures in various computer vision tasks. The paper did some experiment by using different kinds of shortcut, but identity performs best. Why does it have to be identity? There is no explicit reason for it, but with plenty of experiments, it proves that identity is the best shortcut, which is hx equals to x. And the branch of this block is called shortcut. Some people think that the identity part is the main path, and others think that the two conf layers is the shortcut. In this paper, the author thinks that the identity is the main path. The ResNet is constructed as this table. The max number of layers could be 1001, and it was a very stunning experiment result. But even though it can go to 1001 layers, we only use up to 152 layers. And sometimes we use 152 layers for computations so as to improve for 1 or 2% of accuracy. But most commonly used is 50 layers. Now let's take a look at the ResNet code. It is very simple, just as its theory. So I have two conf layers, and each of those conf layers are followed by bn and relu. And for the forward function, I first store the input feature map to identity, and then the input feature map also goes through the conf bn relu and conf bn again. And then if it has downsample, we downsample the output, and then we add the output of the original x and the output after two conf together, and then we return the out. Based on ResNet and group conf, here came the ResNeXt. It widens the network. Because group conf can reduce the number of parameters, under the same number of parameters, we could add channels to make the network wider. For example, if for ResNet the number of channels is 64, then it equals to 4 times 32 groups in ResNeXt, which is 128 channels. So it widens the channels, but still keep the parameters relatively small. In the year of 2017, there came the DenseNet as well. It uses the shortcut idea from ResNet and uses it everywhere. ResNet is using shortcut every 2 layers. There is an identity shortcut, but in DenseNet, all layers are connected together. It means that all layers have residuals. The idea is pretty straightforward, but the effect is also very obvious. Because shortcuts don't need parameters, it can keep the number of parameters very small, but make the network very wide. But there is one drawback. Because shortcut takes time, even though the network is small, the time it takes may increase. From those two charts, you can see that the number of parameters and the number of flops are relatively small for DenseNet compared with ResNet, but the error rate is also smaller for DenseNet compared to ResNet.